So without wasting time, I should straightway go to the presentation mode.
Sir, can we take one photograph before start? Yeah, yes, sir.
So everyone, please turn on your cameras. All the participants. Sanjeev sir. Thank you, sir.
So may I?
Sure, sir.
Yes,
Sure.
sir. Yes, sir.
Okay. So welcome to all the participants, and I am thankful to Dr. Vivek who has given me this opportunity to speak before you. Hopefully you're not going to sleep within this 2 hour session, because in the last half an hour session you are to speak and I'm to listen. So hopefully, based on whatever I speak in these 2 hours, based on that only we are coming to the conclusion in the concluding session after these lectures. So these lectures, if you understand from the whatever topics have been covered, I see that you have covered the basics of reliability. Of course, the software reliability is coming into picture in the very next day or so. So if you understood the reliability functions, so my lecture can give you an idea that whether the maintenance, the kind of maintenance you do, or the engineers do maintenance, why they do it, whether the reliability is improved or not, under what cases it is going to be improved, under what cases it is not. Besides, this lecture will cover some of the very preliminary models which are applicable, they are still applicable to industries. Of course, one can extend those models to by relaxing the assumptions being made by developing these models. But to some extent, they give a very good idea about when to do maintenance, why to do maintenance, and so on. This brief background, I'm just giving you. Okay. So before my slides are visible in projection mode. Hello.
Yes, sir.
Yes, sir.
Sir, it is visible, sir.
Okay. So just giving a brief idea where I serve, as I have already introduced that I have joined this institute in 2003 December. But the past to present here implies this institute, this school did not come in 2003 or so. So it was existing since 1982 or so, right? The reliability activities in this institute started way back in 1981. And then the school has been formed from the grant from the MHRD. At that point of time, it is 1 million rupees. And the founder was and is also known as the father of reliability engineering in India, Professor K.B. Mishra, under whom I did my PhD also. And 2016, this gentleman, Subir Chaudhary, he is a quality guru, very renowned person, and the chairman and CEO of his ASI Consulting Group. He's heading that group. And he is an alumnus of IIT Kharagpur, probably 1992 batch. So he In fact, you know that IIT alumni are providing some kind of grant, donation or so, propagate certain areas. And since he's well known as quality guru, so he wanted to expand the proliferate the quality education in India, which he says that it is still at very preliminary stage. Even we say that reliability is still is not well known in India, but last 5 or 10 years, I'm seeing that everybody is coming to learn reliability and of course the quality. Okay. So this is just a map, road map since 1981 to December 2016, and now you know that this is February 2023. So 2016, the center was recast into schools of quality and reliability. The reason I have already given you why it has come, because reliability and quality and many other engineering subjects can go together, they can complement each other. So with this brief summary, I just, this few slides just leading to what you have learned so far, and possibly this is again complementing to the knowledge you have gained for the last 2 or 3 days or so. So reliability is usually deals with the random phenomena. In our case, we are going to do the time to failure, which is random in nature. Nobody can predict when the failure is going to take place, but to some extent, we can say in a probabilistic manner, we can say that yes, the chances of such events happening is this and that. So we are dealing with a random variable whose values are known, or a function. You will find this definition in many textbooks, or a function that assigns a value to each of the experience outcome, occurrence of which can only be expressed in probabilistic terms. So on the right hand side figure, you will see that on the right hand side, these random variables you can broadly categorize whether they are discrete. You already learned in your earlier classes or might be teaching also, because I know that you are coming from the teaching background. So discrete random variables, they can take the discrete value. And the well-known, whenever you read a since probability book, you will find tossing a coin. This is one of the examples where the discrete events are taking place. Likewise, your dice, the very common example, but in our case, it becomes the expected number of failures is one of the random variable, which is discrete in nature. Likewise, number of spares to be kept. This becomes a discrete random variable. And another is continuous random variable. So in the continuous case, as I said, time to failure, time to repairs are some of the random variables which are dealt in reliability engineering. So those are the phenomena which can be coming from a population of known population can be described in terms of some known distributions. Then we say these are the random. Right. So the functions which you have learned in your most probably first lecture, the PDF, the probability density function, cumulative density function, reliability characteristic, and so on. So why they are going to use? Because they can give a beautiful idea once you analyze the data. They can give beautiful idea about the phenomena underlying the failure process or any other process. So if you talk about PDF, which is measure of the rate at which failure occur, or on how and where the failures are distributed or concentrated, where the CDF describe how the cumulative number of failures are distributed over a period of time. Reliability characteristic, you can define it here, here through either user definition, or you can say in a qualitative way how fast the reliability of a unit is decaying over time. What to do, how to recover this decay in reliability. Besides, once designing the system, this characteristic can be compared with the targeted value, whether the current design meets the reliability or not. Or during a period of maintenance action which we have taken, for example, we are going to take the replacement decisions. Then during this period, the reliability requirement, whether it is going to be matched or not. So if you, I'm sorry, I'm just suffering from coughing cold. Hopefully there will be slight disturbance of this kind of noise. Please excuse me. If you see the characteristic, this is a representation of PDF, this one. So right tangent area, which is shaded area, it means if we talk about the on x-axis, the time to failure, whether it describes and how this failures are distributed, then if we say this area, then with that we read this area like probability of failure on or before this time. So that we call that CDF, right? The area under this PDF curve, where the right hand area becomes probability of not failing on or before this time t becomes the reliability. That's what we do not want any failure on or before a certain mission period, right? Of course, the other conditions, the conditions of use and the intended functions are implicitly one can mention. So on other this the another factor which you know, that hazard rate known as instantaneous failure rate. Many of the textbooks confuse you that failure rate and hazard rate same, but if you examine the definition critically, you'll find no, they are not same. Only instantaneous failure rate you can call that hazard rate, and this describes how fast or slow the surviving members of a part population. So remember, it is with respect to the population on an average, how these surviving members are failing. In other words, how hazardous the situation is, what to be done. Okay, so this gives you a curve, which is a well-known curve known as this Bartle curve. Right? The shape of this is similar to the Bartle, or almost similar to, where the y-axis say the hazard rate and with respect to the time. So initially it decreases, then comes to the stabilization period, and then it starts increasing once the system gets easy, right? So if you have the data, which I see you are going to cover in some lectures, analysis of failure data. So even analyzing the data in a non-parametric manner, one can guess the failure process that can lead to the more advanced data analysis. So most probably that is going to be covered briefly in your subsequent lectures in this course. So those factors, another failure has to be defined categorically whenever somebody wants to do the reliability analysis or reliability study of any product. So you will find several definitions. People have defined depending on the area they are working on for reliability study. So you can say that one definition could be, which is given in millistandard 721. To give you an idea, these are the military standard. You will find on the net also. Initially, the reliability, in fact, engineering started from the military applications only, and the post World War II. So military standard, they are defined various aspects of reliability in defense products, and then later went to the other areas like safety area and the automobile area, then now consumer goods also, right? So an inoperable state in which any item or part of an item does not perform as specified. Or you can say it does not perform its intended function. You can call it a failure. Another definition you can say given by recent this IEC, there are another standards which is given by International Electrotechnical Commission. So you find the definition of failure is the termination of ability of item to perform a required function. You can see that more or less these definitions are similar in nature. Okay, so and as I said, people have defined different types of failures also, a critical failure, a combination of failure, or dependent failure, and so on. So various definitions you'll find, but once you're defining a failure, what about these aspects? Suppose the voltage which is coming, which should be 220 plus minus something, it deviates from that value, specified value, whether you can call that is a failure, or something is supplying low power. For example, the bulb, right? It should give a 65 or some lumens of light, which is not supplying. It is glowing in a law, whether you call it a failure. The second example, you can say the low fuel economy in your vehicle, whether you are going to call a failure. And other, you can cite many. So it depends on how you are defining a failure while conducting a reliability study. So remember this, failures has to be defined, or failures are to be defined once conducting a reliability study. So you'll find there is a categorization of failures, intermittent, which is self-explaining, that it is occurring. Some conditions are matching out and that failure occur, and when condition is removed, that so you frequently find this kind of failure in your operating system, right? So Windows sometimes is not working, you are rebooting it, right? Software failures can be called intermittent failure, and many of the times you will also find in hardware also. Right. And the next is extended, where one has to take certain maintenance action. So complete failure and partial failure. So complete failure, you can say that it is the definition that it is the activity has been stopped. The system or the item is not functioning at all, so it becomes a complete failure, where partial part of the functions are not done by the device. For instance, your mobile, suppose it is not its camera is not working, but you're able to communicate each other. So you can call that as a partial failure, and that is for many of you that may not be a very say critical failure, but many of you might be. This is a critical failure. You are able to take the photographs, right? Likewise, you can define this partial failure. Under partial failure, you will find sudden failure. Sudden means there is no warning. There is no warning. Suddenly something fails. Where there's gradual failure, there has to be some warning. There, that you have to take this action. If you're not taking action, and that is going to lead to the failure, which you agreed upon the definition of that failure. So now, if you combine sudden failure with complete failure, complete and sudden, then we can call that catastrophic failure. And once you combine partial and gradual, then you are going to get the degraded failure. Okay, there could be other failures definitions from the stress system theory. In fact, this is very much applicable to the mechanical components and other structures where the gradual failures are gradual degradation is taking place at one point of time, they fail. For instance, you have at t is equal to 0, the strength is very good. You have designed a very good system with good strength, assessing of the stresses that the stress is not going to be such. But over a period of time, the strengths start decreasing and the environment or the stresses also changes, right? And at one time, they interfere each other, and more they interfere, more the chances of failure. Okay, so this interference zone gives the probability of occurrence of failure. So this is another area you can find possibly. I don't know whether it is going to be covered in that, but this is a stress system theory approach for reliability analysis. You will find once somebody does, you might have heard reliability centered maintenance. So failures, of course, can be defined. They have defined again the failure in different categories with safety consequences, with environmental consequences, with operational consequences, with non-operational consequences, and so. So a slight definition, a change in the definition might take place, but as I said, failure has to be defined in a more categorical manner. So from the bottom curve you have studied in the previous lectures. So what we say in reliability, because failure happening is a random phenomena and can occur at any point in time of product's life, but they always have a reason. So they can occur predominantly in the early life of product once somebody is launching the product or so. So these are mostly when the manufacturer is very complacent. He has done every testing. He knows the environmental condition where this product is going to work. He is complacent that yes, my product is not going to fail and the process is in place. But if they are failing, so we can say that they are related to quality related failure, and most common you will find catastrophic or sudden failure which can occur anytime in the life and are due to accident without giving any indication, right? And you can also analyze those failures with respect to SS theory, as I mentioned just before. So most common you will find catastrophic or sudden failure. Mostly you will find in the electronics equipment. Suddenly one fine morning you will find your mixture is not working, or there's a machine. Suddenly your TV is not operating, your Wi is not operating. So catastrophic. They did not give any kind of indication that yes, we are coming. Then comes the gradual or wear out failure. So this you already say over a period of time, the strength is weakening and aging. Humans are also going through that only. Gradually the strength changes as we age, as we start doing a kind of maintenance, regular visiting to the doctor, identifying the parameter, testing of the parameters, whether they are under control or not, and so on. So likewise for the engineering product, similar thing happens. So degradation indicators such as crack growth, change of resistance, corrosion. So this part once turns out, this becomes an ideal for preventive maintenance or condition-based maintenance. Right? This is one of the reasons you can find that why we do maintenance, whether it is any type of maintenance, except the corrective maintenance. Corrective maintenance, of course, you're doing it once something has happened, you are taking reactionary measures. You're only working reactively. That something has happened, then only you are waking up. Okay. So this just give you the idea, the regions. One can divide the hazard function into three zones. First is the infancy, another is useful life, where in infancy there is a decreasing failure rate, right? Decreasing failure rate, where the useful life governed by the constant failure rate. Right. The possible causes have already been have also been identified. As I said, the infancy period, the quality related attributes can be given, and the reasons could be due to this quality related failures. The possible improvement actions one can take, better quality control, acceptance testing, and there are tests known as abundant test, environmental stress screening, or highly accelerated stress screening. So there are ways over a period of time researchers have given that the first part failure can be reduced, that is before they reaches to the customer, they should be removed at the very early stage. The second is CFR, constant failure rate, of course, because this is random in nature, load is exceeding or due to human errors, or it can be attributed to chance events, acts of God also. Suddenly some spike is coming, or some flood is coming, or lightning is striking, or so the new term resilience is coming up, and reliability also. So you design a system which can sustain these kind of disturbances, right? The third part, so this gives you this is a battle curve, which is a culmination of three types of failure. This is the initial failures, which is attributed to the quality related failures. They gradually coming down once the items or system ages, right? So weaker components are dying and they are replaced by stronger components or better components. Hence, this kind of earlier failures can be reduced or using the quality controls. The another is the constant failure. They can occur, whatever do, because they are random in nature, what happens, what not. So they can only be addressed through the design, right? Redundancy is one, robust design, strength should be sufficient, right? And the third type of failures are, these are the failures which are gradually occurring when the system ages. They are becoming high and high, the system aging. And so you can divide this early age, youth or old age, or you can say phase one of this battle curve, phase two of the battle curve, phase 3 of the idea is the every type of failure is present in throughout the life cycle of a product, and a combination will give you this kind of shape you combine them. So we try to eliminate these failures, we try to eliminate these failures, we try to prolong these failures, occurrence of these failures, right? So as I said, there are design methods and reliability which are assisted, which can be applicable to remove this, and this is the third, right? The increasing failure rate. So here you will find we resort to the preventive maintenance, right? So our zone of interest from maintenance becomes this area, and I will show you why this will not be this, why this will not be the area with the maintenance. Are you going to be benefited taking any action, maintenance action in this zone or this zone? So these are some more definitions. The fault, I'm not dwelling upon one because whatever useful for you, of course, this is useful reliability engineering. For this lecture, possibly this is not useful. So I'm just giving you a kind of input. Yes, there are other definitions which are applicable on many occasions once you conduct a reliability study. So fault is a state resulting from a failure mode, the manner the item is failing. Right. Once possibly you have heard of failure mode and effect analysis, where once you formulate the sheets, you are to fill the possible failure mode through an item can fail. For example, just a simple example of valve or for diode or a switch. Right. The failure mode could be open circuit, short circuit, right? This kind of failure, you can call that failure mode. The manner depending on the use of the valve or use of the diode that can fail, right? Short circuiting diode, open circuiting valve, and so on. Then there are, once somebody identifies the manner, then one should try. If somebody is to improve the system, then one has to go to what could be the possible causes so that the appropriate measures can be taken. So these failure causes can be attributed to any of the area, right? It could be the design, it could be manufacturing, or it can be use or misuse. Right. So there is a complete category one can find out. In fact, one can find out the root cause, whether it is design related, whether it is manufacturing related, or whether it is use or misuse related. Okay, so these are just information on such know-how initially, right? So a complete, possibly this, whatever slides I projected, you will find in this book by Avalash Brisky and DNP Prabhakar Murthy. They have given many case studies also. Once you, okay. So, but initial part, you will find that these are the definition you will find, which many of the textbook does not have. Okay. So coming to the topic, with this preliminary preventive maintenance in its quantified advantages, that is related to the reliability function, AMTTF function. I hope that you know the reliability function, the PDF, how you find out the mean time to failure or the reliability at a particular time. So that is related to once you are not doing any maintenance. But if you do preventive maintenance, if you're doing some actions preventively, then whether the reliability improves or not. So this is the idea on this. Yeah. So the reliability centered maintenance, you can get the answer to the question, what type of maintenance action needs to be taken in a nutshell, right? I'm not going into the details of reliability centered maintenance, but one can get the idea what kind of maintenance, whether it is correctives to be that is run to failure, okay, you need not to do anything, but preventive maintenance to be taken for another component or condition based maintenance to be resorted to. So you can find out what type of maintenance policy or the action should be undertaken. But it does not give you an idea when to perform the recommended action. Okay, so that comes at how to find out such time when such actions could be taken place. So traditionally you'll find the practitioners are expected to cope with maintenance problems without seeking to operate in optimal manner. So some of you might have observed, Sanjeev is also a witness to that. Okay, manufacturer has given, you do it 3 months, 6 month interval, like we do for our vehicles. Once you buy a vehicle, he says that come after 1 month, certain preventive maintenance is to be taken, or you do preventively each 1 year, something is to be changed, and so on. Without, so many of the occasions I asked from this Maruti dealer also, I am seeing that filter is in very good shape, apparently. Visibly it is in good shape. But what parameter you observe to replace it each and every year? But I did not get the answer. Sir, change kar dena chahiye. Right? So that kind of answer you will get. Okay. So there is always certain constraint. There is certain objectives also. And we have to find out a solution which can give us the best, that is, outcome. So we have to set out certain variables. We have to satisfy those constraints to optimize the objectives set out. Objective could be anything. For our case, it could be minimization of downtime. It could be maximization of availability, minimization of loss, maximization of profit, and so on. Once you do with everything on cost basis. So attempting to resolve the conflicts of a decision situation in such a way that the variable under the control of decision maker take the best possible value, you can call that optimization, right? In fact, you are searching the space to find out the combination of the variables which are not only satisfying the constraint imposed, but also giving the maximum benefit, right? So this is optimization, and based on this, you can say that we take some kind of formulation of the problems, and then we try to get the value of the variables so that our objectives are fulfilled. Okay. So this is the thing, right? Okay. So most often you will find that despite availability of the data in plenty of the organizations, this is computerized maintenance management system or asset management in the enterprise asset management system or ERP. Managers are not knowing how to use this data there, right? How to use the data despite having such a data. In many of the occasions, we also face this problem to segregate the data and then find out many of the times the data is in such a bad shape that even it can take 1 year to resolve that issue. So there is always a keen interest in evidence-based maintenance decision rather than based on just a gut feeling that, okay, it appears like this, you take this decision. But there has to be, so evidence-based maintenance decisions are, you are hearing this PHM, right? Probabilistic health management systems are coming up. Based on that, they are giving the health indicators of the system, so, and then based on that, analysis and final what to be done. So you'll find many of the areas where this maintenance or decisions are to be taken. Some of the problems you will find in the replacement rules for components or capital equipment. Right. So capital equipment, in fact, they are just dealt based on the cost criteria only, not in a probabilistic manner. Okay, cost based, but components, of course, they are dealt with both deterministically and probabilistically. So to find out optimal inspection frequency is another area where the models you will find, then overhaul intervals, another area, whether to repair or replace, what decision is to be taken. This is another area, then repair queue size, composition of machines in a workshop, rules for spare provisioning, and so on. There are many areas which comes under this maintenance engineering category, right? So in this lecture, mostly we are dealing with this, right? The highlighted part, not other area. Okay. So common approach to adopt preventive replacement of critical components within the system, and the failure during operation may be much more expensive because it is unannounced, unscheduled. Suddenly something is, so there is assumption if we do not know this preventive measures, and failure is occurring, of course, the cost is going to be very, very high. This is one of the assumptions to go for modeling or do the maintenance exercises. Right. The idea is very clear because suddenly something is happening which is interrupting the operation at an undesirable time, and a failure part may damage many other the components within the system itself. So this is one of the reason why we do the maintenance. Okay. So reliability of an equipment can be increased substantially by preventive maintenance, whereby units, as I said, enter its wear out life of or age it. And the system ages, we say that reliability can be improved through certain maintenance action. Okay, so this is so so they can be replaced with new units at predetermined period of operation of the unit itself. That is, unit is operated for a month. Okay, we can now replace it, or based on the system has itself is operated for 1 month. So there could be two possibilities. Okay, so items its own age or systems age. They are two different things. Now, the objective functions might be minimization of the cost of operation and replacement, or minimization of downtime due to failure replacement and preventive replacement. So these four models one can generate immediately. The combination could be this only. So the idea is to reduce the average failure rate or average cost of failure, downtime reduction, hence increased availability and productivity. Total maintenance man hours, of course, number of failures are more. This maintenance man hours are going to increase. If you are if you are not optimizing the preventive replacement interval, might be you are doing over maintenance or under maintenance. Depending on that, you are using or misusing the man hours, right? Secondly, if the design reliability of the equipment is not adequate, which is not satisfying the need, then operational reliability may be increased substantially. Okay, so these are some of the points which advocates to do maintenance. Now coming to just give you an idea, what is the effect on Barter curve? If you see that, if you call that Barter curve, and at this point, if you do the preventive maintenance, the failure rate has decreased. Then again, after some time, it starts increasing, right? So overall, it is increasing only. So if this kind of feature is coming out, that after some time, again, the failure rate increased. So this is not a proper schedule of preventive maintenance, because after a certain time, again, it starts increasing, right? So this gives you, that is why we go for this, to find out best possible interval at which the maintenance should be taking place. So if the PM is not done properly, sufficient reduction in the failure rate may not be affected, which is shown in this figure. In this, if somebody is not doing the preventive maintenance, then this is the Barter curve, hazard rate is increasing. But if somebody is doing the preventive maintenance, failure rate is decreasing, and it's kind of adulations you will find. And if you take some kind of average, okay, so average failure rate has settled down to almost a constant value, which is of course more than the value of in this useful reason, right? So if the preventive maintenance is not good, you will find this kind of. Preventive maintenance is good, then you will find this kind of scenario. So this is, you can say, the concept behind the doing the maintenance action, right? So confusions you will find, which component should be considered for preventive replacement and which should be left to run until they fail. As I said, there are paradigms which gives you answer to these questions. RCM is one of the approach one can go. And if the components comes under PM replacement policy, then what is the best time? Okay, so this will answer in these two lectures, right? So the problems can be classified into deterministic, as I pointed out, and probabilistic or stochastic. In the deterministic, The actions is known and outcome is known. That if you take this action, this will happen. In probabilistic, you take the action and the outcome is by chance. So hence you can only deal with probabilistic manner. Right? Just to give you an example. Replacement of a component that deteriorates deterministically. You know that once you, as I give the example of automobile, you're changing the filter, the mechanic will say, sir, it will give you better performance. The cooling will be better. The cost is also going to decrease. Okay, so this item is being used over a period of time. You will find the cost of operation is increasing. And at this point, we say that, OK, we have to replace it. OK, so replacement is done. We know that since we have replaced with the identical one, the cost scenario is almost identical. Right. So this is known that this will decrease the cost and the cost variation will be like this. So this could be fall in the category of deterministic example. You might cite many other examples based on your own experiences. Right? How is deterministically like? I can also cite other example other than this filters. You know that one another example which I said that change of filter of AC in the automobile, right? And many other from your daily. Of course, electron component you will find anything is changed except that you are changing the filter of your water purifier on a regular basis, either cleaning that is another maintenance action, or you're directly saying, OK, replace it because it is now worn out. It is not filtering water in a proper manner. Right. So some of the sample fuel filter, brake and clutch module, paper mill file, molds for glass production, and so on. Right. So these are some example. Of course, we'll see two models for that. So in probabilistic paradigm, you will find what are the uncertainty involved to take such a decision for probabilistically failing equipment. Right. Suddenly something is failing, all period of time is failing. Right. So in reliability theory, whether you're a newcomer or you're expert in that, it is almost impossible to predict when the failure will occur. Yes. No one can predict the failure. Right. For human also, you know the life insurance based on prediction only they are doing some premium or so. Had it been so, everybody would have planned their life. Okay, we'll do on this year, that year or so. So the impossible to predict when the failure is impossible to predict with the transition from one state to other state will occur. It is almost impossible. Right? When it is going to go to bad state, that is failure state, or bad to this state, post repair or replacement. It's very difficult. Impossible to determine the actual current state of an equipment, good or bad, in between or them, unless a certain maintenance actions such as inspection is taken place. So in most of the models, since I said these are, I'm going to discuss basic models. Of course, one can go for the advanced models. So in stochastic replacement model, to reduce the complexity in the model, as I said, keep the model as simple. In the very first slide, you'll find keep the model as simple as you can. But it should give some kind of plausible or feasible results, not the vague results. Okay. So in almost all the models which we will discuss, there are only two possible conditions of an equipment: binary state model, functioning, not functioning, good or fail. We can categorize that. And condition is always known through certain other maintenance sections such as inspection. Right. So optimal say, okay, this will. So in most of the models, or rather, of course, some of the models, because these assumptions have been relaxed also, it is assumed that after the replacement or repair or overhaul, the equipment is returned to as good as new condition. So the assumption implies, so various cost, the failure process involved, and other criteria are identical to the replaced item. They are remaining same. You will find these assumptions as bad as old also, in between also. So there are models for such cases also. This is as good as new, as bad as old, then intermediate. So there are other models as well. Of course, that comes under repair system modeling and analysis. So the last point only says that if overall and repair also in these models, which we'll discuss, are taken as or returning to the item as good as new. Now coming to the point that reliability under preventive maintenance, reliability function you have studied, but can we derive the reliability function under preventive maintenance? What changes are going to occur in that reliability function? Okay, so whenever we are doing preventive replacement, there could be there could be possibility. One is there is no failure during the replacement interval we have decided. So no failure case, right? Each time it is replaced at this point, this point. But there is a possibility that before we replace it, this item fails. And as and when it works for up to certain time, that the age of this item, that is what I wanted to differentiate. One is item age, this is item age case, not system age case. So when this item say lives for certain age, it is going to replace, or there could be it is failing here, replacing here, again it fails, right? Again it fails and replaced after certain age t, right? So these are the scenarios which can depict under this. This is just the explanation of these figures. So I need not to reiterate on this. Okay. So you know the PDF, as I pointed out, that the reliability is the right hand side area. We are replacing it here. Okay. So this zone is impossible in this case once we are replacing it. Right. So this is reliability area, though it is, and we are replacing it at this. So failure can occur on or before this 0 to TPR. So if you see that, you have seen that if the PDF is known, how you can compute the MTTF. But in this case, you're not taking the entire PDF of that item. You're taking the item. This is truncated kind of thing. Now the failure can occur when in this zone only. So you have to find out the mean time to failure once the item is going to be maintained preventively at each TPRs. Okay, so this is the difference once we conduct reliability. So the probability of a failure is the probability of a failure occurring before time TP, which is unshaded portion. And here we need. Okay, so the complete, if you know if you're taking into account, you're not doing any maintenance, then you know that how the MTTF is to be computed. And now what to be done so that we can still compute the MTTF for this case, right? Earlier case is this, now this is the case. So reliability function, coming to the mathematics part. I hope you are comfortable with the mathematics. Hello? Can I hear some yes or no?
Yes, sir, comfortable.
Haji?
Comfortable, sir.
Good. So what you're doing, देखो भाई थोड़ा हिलेगा कोई प्रॉब्लम नहीं होनी चाहिए आपका ये टाइम पीरियड है राइट दिस इज द टाइम पीरियड where your item is to be operated and you have to do it is to be replaced preventively at some point of time, which is to be determined TP. Right? TP. Each TP, it is to be replaced. And this is the time scale, right? You have to operate this item for some time T, right? And if you're not doing it preventive maintenance, you can, if you know the PDF reliability function, you can easily find out what is the reliability of this at time T, R of T, which you call that. But if you're doing preventive maintenance, then the reliability is going to change because it is to be replaced or repaired, bringing it to the as good as new condition. Then under this condition, how the reliability is changing. So assume that this time period is 0 to tau. Once it is reaches here, it is replaced and the clock is again reinitialized to 0. So the time period in this interval is tau and TP is reached and so on. Am I clear? Am I clear?
Pardon, sir. Sir, can you just repeat it once again? Can you explain it once again?
Right. This is the operational time, right? T. Okay.
Sir,
Operational time T. So you can find out the reliability at time T if you know the PDF and other functions. Okay. R of T.
okay, sir.
R of T you can find out. But now what you are taking, you have decided, okay, this item is going to fail. My operation is hampered or interrupted. So I will replace this item within the system, right? Replace this item. Say, for example, the filter you are going to replace at each some interval. The interval is say TP. Okay.
Okay, sir.
And this tau is another variable is varying from 0 to TP. Once it is replaced here, the clock is again set to 0. And again, we say this in between, this is varying from 0 to tau.
Clear, sir.
Right. And this is J is equal to 1, first preventive action. This is J is equal to second preventive action. So this becomes J is number of preventive maintenance actions. Right. So T could be equal to J number of maintenance action TP plus tau. If I say that, suppose this is the last action which we are taking and this is the tau, right? So this T is number of replacement we have done. And now whatever the time post last preventive action. Okay.
Okay, sir.
So this is the notation reliability at time T when the item is changed at each TP time. Okay, understand the symbol. Okay, at each TP hours, day, whatever time units one has taken is changed. So otherwise you can always use the reliability R of T. Okay, so this is notation. If you are able to understand, then everything will be easy. So reliability at time T can be reliability at. Okay. And at each interval, what is reliability at this point? R of TP. Right. R of TP first change. Okay. In this interval. Then now the reliability of the system is start at this value. And again, the second interval is start. So reliability will be RTP into RTP, the second time interval. And beyond that, R tau, where tau is again, remember this is 0 to TP. When this is reaching, then it becomes the third replacement. So reliability equation changes to this. Well, okay. So this is one of the equation. Am I clear?
Clear, sir.
हाँ यार थोड़ा हाँ हूँ करते रहो, दिखाई नहीं दे रहे हो, विवेक जी ने फंसा रखा है. Only talking to the screen. थोड़ा टाइम भले ही लग जाए, but at least there should be dialogue, not monologue. Okay, so this is in fact the reliability equation changes. Okay, we'll see the application also. Don't worry. Although the time I am saying that already 50 minutes are over, but I will not go to the derivation detail. Okay, please, you can you can easily understand that. I will give you just an idea how that can be proven, right? Then the mean life, the another factor is MTTF, whether MTTF also change. So this MTTF, you know that if you know the reliability function, if you integrate it 0 to infinity or minus infinity, because T minus infinity is not in our case, because T always we cannot go in the past. So 0 to infinity and integration of this. Right. So this equation should replace here. And the integration part, of course, you know that you have to find out the area under the curve of reliability when preventive action are done. So this can be, so one can resort to the piecewise integration. I hope you can do it. If you are not understanding, I'm just skipping right now, but you are always welcome to contact me how it can done, right? This is just the derivation of that. And finally, which turns out to be the geometrical progression, infinite geometrical progression. So this is the equation is of our interest. The mean time to failure, when the item is replaced preventively at each TPR is given by this equation. So remember this equation, and I heard that you are to say you have to undergo an exam also. So remember these equations, the application of these equations will turn out, right? The earlier equation, this reliability equation, and this equation. Remember these two equations, the reliability under preventive maintenance and mean time to failure under preventive maintenance. Okay, so these are the two. So just one example, we can see. Okay, I'll see that how much I can explain you this example. So usually it is said that if a single unit following a constant failure rate, whether maintenance is justifiable. So we say that no, it is not justified. As I explained, one can mathematically prove it. In my slides also you will get the proof. But suppose there is a redundancy exists. Two units are being used in active parallel mode and any other mode, redundant mode, whether the maintenance is justified. So answer, you will see that yes, we'll have to do it, because once we use the redundancy, the hazard rate is not remaining constant, but it starts increasing. To find out the hazard rate of two units in parallel, which we have gone through the reliability modeling part, right? Take some value, constant value, lambda 1, lambda 2, and then plot with respect to time, you'll find that the hazard rate is increasing. And as we say, once hazard rate increasing failure rate, then we say that we have to do maintenance. Right? So with no maintenance, you will find this equation, well-known equation, identical units we have taken, where failure rate is equal to 0.01 failures per hour, right? Or MTTF is equal to. So just put this value and use this equation and take the different value of TP. Okay, one can take the different value of TP based on this. Okay, 100 hours. Okay. Can we do 10 hours? Can we do 50 hours? Can we do 150 hours? Can we do 500 hours? So what is the impact of doing this preventive replacement at different hours to see which could be the possible, right? So this is just, you can find out what the equation for under preventive maintenance, right? The unit, this is two parallel unit system under preventive maintenance. Okay. So when J is equal to 0, that is, you're not doing any preventive maintenance, and the time to do the preventive maintenance, it implies that TP is almost very large. Followed? Hello?
Yes, sir.
TP is very large. It means you are not doing it all. You are not resorting to preventive maintenance. So it is nothing but the original reliability equation one can find out, right? So tau is now varying from 0 to infinity. So you will get this reliability equation. If you do every 150 hours, you will get this equation. This is just substituting the value. And varying T, what is the variable in this case? Tau. Tau you are varying in between 0 to 150 hours, and see the reliability, how the reliability is varying. I can show you this picture, right? When T is equal to 0, you are replacing it, that is theoretical. Theoretically, it becomes the reliability is almost setting to close to 1, right? You're not running the system at all. Right? You're just taking it, replacing it with a new and so on. So you're not using it. So reliability is, but if you do the reliability, if you're not doing any maintenance, then the reliability curve is taking like this. Can you see the cursor? Hello?
Yes, sir.
Yes, sir. Yes.
So you see the, when you do instant replacement and you do not do any replacement. Right. So whatever is going to happen in between these two curves. So if one is doing, for instance, at each TPRs, so the reliability curve up to 50 hours same. Now the action is taking place, then it deviates. And each TPRs deviates. So if you want to see what is the reliability at this point, so obviously the reliability once someone is not doing preventive maintenance and someone is doing preventive maintenance, a substantial increase in the reliability is going to observe. Okay, so other curves are similar to once you do it at each. So how much reliability improvement is to be needed depend on what is the target reliability. So one can decide what will be it, right? So this is just an explanation to the curve, right? I'm just switching over to the next slide. Is it okay?
Okay, sir. Sir, I have one query, sir, please.
Yes.
Like, sir, the just diagram you shared, let's say, sir, I have a specific, or if we consider like I am supposed to use the equipment only for 100 hours, let's say, sir, and the desired reliability, let us assume, is only say 0.4, sir, to my system, overall system. Then in this particular case, I can go without the maintenance also, right, no, sir?
First, you are saying reliability is 0.040.
I'm saying, sir, I just want to use the specific system for 100-hour life, and let assume that I will do it under beyond economical repair. I will just scrap the item, and the reliability requirement for me is only 0.4.
Reliability requirement 0.40. What does it mean? Right?
Mission reliability we are defining, which is decreasing with time usage of.
What I'm saying, there is only 40% chance of that item going to complete the mission.
Right, sir.
So if you are agreed, you can go for it.
And sir, actually, my actual query is like here this TP, which is 50 hour or 100 hour, sir. It is basically defining that what kind of reliability you will achieve, right, sir? So once
defining, it is first, it is defining that what is the impact of doing preventive maintenance on reliability. These are not optimum. That models one has to generate. They are just to show impact of doing preventive maintenance, right? Otherwise, whether it is good, you are just doing preventive maintenance at 10 hours.
Sir,
there has to be some criteria for selecting these wells. Which we have not come up, right?
Sir, what I just want to know is like, let's say for an example for generator, sir. Let's say OEM defines some oil need to be changed for every 6 months.
Yes.
That time period he has calculated that every 6 months, that with respect to some amount of mission reliability.
Yes. Have you ever asked?
No, sir.
That is what I'm saying. So once I have saying that, then manufacturer or the supplier saying you do this, but we never questioning. And out of the fear, only we are doing, oh, he said that it will be. Okay. So many of the occasions, we never ask on what basis you are saying 6 months. Why not 5 months? Why not 8 months?
Yes, sir.
Okay, so there are certain criteria in fact. Somebody should ask us. As I said, we hardly find those answers. As I have given you the example. I can show you the filter also, which I am still keeping for my wiki. Okay, many of the equation, they are not supplying that information. They might be taking based on the just experience, no quantified assessment analysis. No, nothing.
Sure.
Okay. You will find many of the examples. I'll give you the textbook name where you will find out the example, what kind of data is created, how this can be analyzed. Even possibly in this also, you will find one of the slide. Okay.
Okay, sir.
Okay. So we will always try to have high reliability. You can say reliability is 0.40. So how it can be improved? So if redundancy can be applicable, yes, you can go for redundancy. That is reliability improvement. Because during that period, you are saying 60% chances of failure. Nobody will accept. At least I am not going to accept only 40% chances. I will say, okay, no, there should be 90% reliability. Preventive maintenance comes afterwards.
Sir, actually, this is what I want to say is that with the whenever they are claiming any OEM, like after 6 months you should replace it, and then there should be an additional information attached to that it will help you to achieve this much of reliability, instant reliability.
Are they providing you any quantified figure? No.
Nothing, sir, nothing.
Nothing. I know that. You do not have quantified value. Right.
Because there may be a case, sir, because there may be a case like there may be a case like where I am using that particular system. It may be part as a subsystem to my overall system, and my overall reliability requirement might be more. There may be a case like my TP is even less than what the OEM is defined, or there may be a case my desired reliability is less, and then I can go extend to that. Sir. Why I need 0.99? There may be a case.
Always there is a user requirement, right? We are dealing with the defense equipment. User supply the information to the labs. We want this much reliability based on they make the design, and we do the reliability study. Okay. Once we are a customer, we just buy it, right? Just buy it, and whatever manufacturer or the supplier says, we do it because we know that. As I said, once we never get the answers to those questions. It is only thing that once we ourselves analyze and we say, okay. So many of the students do such kind of project. Once they do go to the company, we say, get the data and do the project, right? How the data analysis can provide you the answer, whether that is okay or not. Okay. In the very first picture I said, the preventive replacement is to take in, you have decided say 10 hours. Suppose 10 hours, but you can never predict whether the failure will not take place within 10 hours or not. Never. The failure is inevitable. It can happen at any point of time. Okay. We cannot probabilistically say you are saying 40% reliability, so 60% chances within that interval the failure can take place. One can take that kind of risk. One can go. Right. So that is what reliability studies. Okay. So if you see that, now coming to the mean time to failure, right? When you're doing no preventive maintenance, then it has become 150 hours. So of course, it is 1.5 times a single unit. If the TP at the preventive replacement is occurring at 150 hours, then it is. So if you reduce the TP, the mean time to failure, expectation of failure is increasing. Okay. So this can also be plotted. And this kind of curve can give you an idea what MTTF or MTBF you want. Okay. Partially, the question which is being asked can be answered from these curves. Okay. Expectation of failure. Okay. So this is nothing but observation from that. If TP is 0, the mean time to failure is almost infinite, which you can see from this also, right? If you are, so it is going asymptotically very high value, right? So, and as the TP is increasing, right? TP is so MTP is decreasing, that TP is increasing. So TP, the time to preventive replacement is decreasing. The MT mean time to failure is expected to decrease, which can be shown. Another point which is to be mentioned here, usually you will find in the textbook that the preventive maintenance is wasteful if the units are exhibiting constant failure rate. But remember that this is not true when there is existence of redundancy, right? Redundancy, I hope that you know that what redundancy means, right? As has been shown in the earlier figure also. Okay, so this is just reliability under preventive maintenance is going to be much greater than the reliability when no maintenance is taking place. Okay, this is just the point mentioned here. So if you see the exponential, the reliability of the unit with preventive maintenance ability figure is not any different than. So under the CFR case, you're not going to get any benefit. You can prove it using these two equations. Right? Using the earlier two equations, one can prove when the failure rate is constant, then there's no benefit. Okay. Proof is given here also, right? I'm just skipping. Okay. Is it okay? I know. The proof that reliability, whether you do preventive maintenance or no preventive maintenance, it is turning out to be this value only. Okay. The MTBF is also coming to the same. Okay, this is another formula which is very important. As I said in the figure that you are settling down to an average failure rate in the Barter curve in the third zone, right? So that average failure rate should be equal to this one, which is the inverse of, you know, that inverse of MTBF is failure rate only. But here in this case, the failure rate, the unit under preventive maintenance, then this formula is to be utilized, not the other formula. And once we allocate the mean time to repair, that is maintainability allocation, then one should use this formula for the unit which may go preventive maintenance. Right. So if it is constant, then reliability can also be approximated to this figure, this equation, right? Reliability can be approximated to. For earlier case, you are using exponential minus lambda t when the failure rate remaining constant. In this case, one can also use this. This was the figure which I was referring to. So under this case, this lambda average should be this one. Okay. Okay.
Yes, sir.
Yeah. So this is for the units which are for beta is greater than 1. You know that the Weber distribution can mimic the behavior in the third zone. So this can also be proven that the reliability for this case is going to be good. Exponential case, and for failure rate in the first zone, which is already decreasing, why you want to do the maintenance, right? This is a simple answer one can get. After all, the maintenance, we try to reduce the average failure rate, and that is already reducing the first zone. Then, so one can also prove using these equation only, right? This is example for this. Right, a bearing. Bearing is a mechanical component where beta, many of the you will find the beta values for various types of bearing people have given in their databases, right? And the characteristic life eta, and many of people are using theta, right? And this is the third parameter, which is the minimum life is 0. So one can find out the mean life, one can find out the reliability at different, right? And once you see that when the preventive replacement is done at each TPR, how much it is 3,99,998, where earlier it was just this much. And one can have different values of TP and see that how much improvement. This is 10 hours, this, right? And it very large value, it terminates to almost no maintenance and in between this. So how does well, right? So the great benefit that result through preventive maintenance at regular pre-chosen periods of operation of units, which have an increasing failure rate characteristic with increasing operating time, like that exhibited by, for which the beta is more than 1. Okay. Surely these are the, and one can also tabulate that, right? This is for the case of T is equal to 100 hours. Okay. So at this point, replacement is done. Okay. At this point, 200 second replacement is done. Okay. So tau you are seeing varying from 0 to 50, then 0 to 50, 0 to 50 and so on. Right. So here the reliability, when there is no preventive maintenance, then reliability is following this, and reliability under maintenance, you will find the improvement, right? Here it is 0.9844, you will find 9944. So this is from the exact equation. And you find out the mean time to failure with approximate equation also you will find the yields are very close to 0.9943, 0.9937 or so. Okay, so many observation, and this curve is nothing, one can draw it from these tables, one can use the Excel sheet to tabulate this. Okay, there is no, if you want to experiment with different types of primitive matrix interval and to see that how these curves can be drawn, one can use MATLAB, one can use Excel, whatever it is, right? Okay. So these are just observation which I pointed out. For example, that approximated using stabilized failure rate with at least a 3 decimal accuracy. This column, right? You will find that. So these are certain observations which I'm just skipping because I'm saying that this is already here. Okay, these are some of the observations, right? Reliability function at different value of RT. So how the reliability, you are seeing the ripples, right? When it is at each TPR. In the earlier figures, all are combined. In this figure, this is only for TP. This is for TP is equal to 100 hours, and so. Another equation. This is the total failure rate. Please always note this equation, right? Earlier equation, I am pointing out what equations are needed in this case. This is the total failure rate when an item is undergoing both preventive and corrective replacement. So you know the probability of failure on or before TPRs, probability of failure not failing is RTP. They should sum up to 1. So this, you can break this equation into these two parts. And first part you can say the corrective replacement rate or corrective, yes, corrective replacement rate, and this is preventive replacement rate. Okay. Is it okay?
Sir.
Yes. So lambda C, which is here, as one of the application is, once you allocate the mean time to repair, the maintainability allocation, this to be used. Another application of these is how many spares are used when the item is expected to fail for correcting. And this gives you an idea about that how many preventive replacement are to be done once the unit is going to be replaced at each TPRs. So spares part calculation one can do from this. One can do, we will see later that one can also develop the models out of these. So these are very important equation. Preventive replacement rate, corrective replacement rate, and the total failure rate when the unit undergo both preventive and corrective. So this is in fact exercise. Earlier we have taken active parallel unit. If you know that redundant system, then you can go in a similar manner for this kind of system where the system is standby unit, perfect switching, no failure in standby mode, right? No deterioration. There are many combinations. This is the ideal case. Switching is perfect, and we are using the main unit, standby unit. Main unit is failing, then the standby unit taking the charge. So for this, of course, the unit we have taken in this case is non-identical, hence why you are seeing lambda 1 and lambda 2. Okay, so this is the equation, reliability equation for the standby unit. Using the previous equation, you can draw the similar kind of curve, take the arbitrary value of that, the TP replacement time, and see that how you can. So coming to the end of this portion. So these are some of the textbook. If somebody wants to learn more on these aspects, one can refer these 3 references. Okay. So the first part over, I don't know how much time it will take the second part. Part of the. So just to have the feedback, I know that to cover such kind of lecture, the time is one of the constraint. And since Dr. Vivek has given me 1 hour, still I have overshooted to half an hour more. And this is a time Friday weekend. You must be cursing me or Dr. Vivek why they have put this lecture on this day. So anyway, so I hope, I'm not saying you understood 100%, but at least I can guess you are going to have some idea that preventive replacement is going to be benefited under certain conditions. From the Barton curve, which is the third zone, from the redundancy point of view, of course, we are going to benefit even if the reliability, the units are behaving in a CFR model or following exponential model. And we can also draw how the reliability is going to improve if we take different time period of replacement. And also how much we are going to gain in MTBF. You can also see whether the reliability goals which are set out for a certain period of time are going to be achieved or not. So this is what I can summarize this lecture, and I hope I am able to convey you this message, besides just avoiding mathematics, whatever I shown, which you can learn later. And of course, if I always say, if you find any difficulty, you're always welcome, because one can use now this the communication media of this kind of Google Meet or this Meet, that Meet. So one can resolve if somebody is not going to understand whatever given in the slides, apart from whatever references I have. Thank you. Thank you very much.
Thank you very much, sir.
Thank you, sir. So before leaving, can we have again a picture?
For leaving, no, we are not leaving. We will come. I suppose I should
Yeah.
come again. I should come again. Isn't it?
Yeah, Vijay. Okay.
Yes, sir. Yes, sir.
We are coming back.
Right. Right. It is hiatus. Just for a brief break, because I saw there was a 10 minutes break. I said I overshoot it. I'm sorry for that, because such kind of lecture definitely takes time. Okay.
It's okay, sir.
So please try to bear with me. And as I said, if you get interested into this area, reliability engineering, I was not a reliability engineer till 99. I got interested because of the type of application it has. And as I said, in the last 5-6 years, everybody is rushing towards, we want reliability, we want reliability. Okay. So just 10 minutes. So at what time we are going to meet? It is 20:30.
Say, sir, 15 minutes.
15 मिनट्स खाना आना खा के बैठना भाई, क्योंकि हो सकता है जब मैंने देखा मैंने 40 slides are going to 1.5 hours, then there are 60 slides. Of course, some of the slides can be developed based on the previous slides, right? So I will see
Okay.
that how much we can go, and I will curtail my lecture at that point, right? Okay,
Right, sir.
okay, so 20.